And boom.
Okay, is everyone on the slides right now?
Is everyone looking at the slides in some way or the other? Put your hand up if you're not looking at the slides in some way or the other. All right, cool. Look at the guy next to you. Or figure it out on your own. I'll give you like, just figure it out. You'll be fine. Yeah, I'll give him 2 minutes then, sure. Count down to 120.
You really made you jaded.
We're just, yes, performance metrics. Yeah, so for those who don't know, we're going to be going over performance metrics today. As usual, whenever I present, it's in no way comprehensive or anything like that, but it's more meant to familiarize you with what performance metrics are used. So yeah. He's also got blue eyes. Oh God. Well, Manny's in here, so it just doesn't even co-host.
Oh, I can't.
Look right there.
Okay, cool. There we go. Yes, I do.
All right.
Okay, does everyone have access to it now? Okay, good.
All right. Cool. So today we're going to be going over performance metrics, as I mentioned earlier. Before we do that, though, Samrat, you injected some stuff about, yeah. Before we do that, Samrat has some stuff to say about the final project. So
yes. Oh, okay. So before the final project, sorry, not before the project. Before the performance metrics thingy, how's everyone doing on the project in terms of like, you know, progress? Just looking at it, just vibing. Okay, cool.
So equivalent project to most equivalent progress to most projects that you would do anyway.
I mean, have y'all met your teams or individuals? You know, okay, cool. That's good. So you're gonna have to finish the project before next meeting, which is the last meeting, which I announced on Pioneers channel. I said in the last meeting. So you're gonna have to finish it sometime between sometime before December 6th. We'll announce the actual deadline, preferably this week. Yeah. So you're gonna have to submit it a little bit before December 6th, just because we have to look through all of the submissions and, you know, judge them and like rank them. Whatnot.
If we're doing it based on a number, just
We could do it in meeting, but it just makes things faster.
if you did ON
Plus
factorial,
individuals.
if you did like an ON factorial algorithm.
Okay. Okay. Anyway, submit sometime before next Monday. Yeah, but what I mean by submit is just complete it. You don't have to put it anywhere.
Yeah.
The only place you need to put it is in your respective folder in a shared drive. If you do not put your project in your respective folder in the drive, you will not be entered into competition and we'll all be sad. So please do that. Instructions are in the document, the collab file, whatever. If you still need help on it, just ask us.
And also, like, for whatever your final notebook is, please have some way of denoting that that's the notebook you want us to look at. So, you know, if it's like, just write like final in the name or something dumb like that, so that it's like, you know, clear that this is the one we should be like, you know, using.
Yeah, in the case you have multiple notebooks.
Yeah.
So yeah, please put your collab files in respective folder, yada yada yada. And after that, I mentioned that there's gonna be a prize, but I didn't really say what it was. So before, you know, we go into this, can we have a drum roll please for the prize announcement? Oh, okay, nice. So if you go to slide 4, oh wait, this is cat drumming. Okay, if you go to slide 5, the prize is a $10 Amazon gift card for each participant.
Sorry, we tried to get GTX 39 or RTX 3090s, but you know, Jensen Wang said he didn't want to pay the passes one, so we're a little screwed.
Yeah. Yeah, we're going with the Bezos way. So essentially, if you're just an individual, you're just going to get a $10 gift card. If you're in a group, each person gets a $10 gift card. So that is how it works. And most probably the person, like the team or individual that wins, will probably like send you, you'll give us your email, we'll send it to you virtually, you know, make things easier, stuff like that. Oh, Gucci, yeah. Any questions about that? Just to clarify, prize will be an Amazon gift card. Okay, cool. And yeah, so we're gonna be Phil's gonna talk about this more, but we're essentially gonna be judging the projects based on.
Oh, yeah, so no. All right, cool. So we're gonna be judging it based on what I could inaccurately call a confusion matrix score. For those of you who know what a confusion matrix is, we're going to just be summing up we're going to be taking a normalized confusion matrix and then taking the sum of the diagonal. and whoever has the highest number of diagonal wins. For those who don't know what any of that meant, I'll go over that today. So you'll understand why I'm doing that first off, and second off, what that constitutes that. So in any case, with that said, I was about to gesture to the giant display. As you can see, it is blank, so that's not going to work out. So I would like to open this up first with a question of, if we're discussing performance metrics, well, what are we going to measure? How should a model ideally like work in some sense? So like, what would you guys say? How would you want your machine learning models to work? No response, cool, cheers. Well, like, I mean, well, how would you want it? I mean, how would you want, sorry, I guess that's kind of badly phrased. More like, how would you want it to perform? So like, in what scenarios do you think, or in what scenarios do you think it should like succeed? And like, in what sort of settings do you think, like, you know, like it's fine if it like doesn't do as well, kind of deal? Okay. Okay, cool. Well, I mean, to put it, it is a very open-ended question, and I can understand the fact that, like, for many of you, that can be kind of a, what the heck is this guy saying? But there are actually, when you're working on machine learning models, certain types of models need to work in or seek to work better in certain settings than others. So, like, for example, if I'm trying to work on a spam detection filter, that's the example that a lot of people use, right? We want it to. Would you want it to be better at classifying, you know, would you want it to be more eager to classify an email as spam, or would you want it to be more reserved, as in, you know, to be much more cautious in classifying an email as spam? Which one do you think would be a better idea? Yeah. So what most people say in that sense is the second one. Why would we say the second one? Well, if something's super eager at classifying things as spam, then it can classify regular emails as spam, right? Now, for some of us, that may seem kind of benign because who the hell reads their email half the time anyway? But for, you know, if for most scenarios, you actually get really important emails such as tax statements and work emails, stuff like that. You don't want those being classified as spam because that can lead to actual serious consequences in life. So you want a classifier that's a little less eager to classify emails as spam. However, if I take a completely different scenario, say I'm working on a model that's designed to diagnose terminal illnesses, right? If I'm trying to diagnose something that's a terminal illness, do I want a model that's more eager to diagnose things or less eager to diagnose things? More eager, correct. And the reason you want more eager is because if someone, I mean, if it's a false positive, yeah, it kind of sucks for that person, but like, you know, it's better safe than sorry. Whereas if you get a false negative, you have a person that literally could die in months and you have given them zero treatment, and that's frankly unacceptable. So there are different scenarios in which we want the models to perform differently. Certain models need to perform better than other models, depending on certain criteria. And so the reason that I asked this question is mainly because, as you can see, there are as I said, there are a variety of ways to define performance, and it is entirely task dependent. Not only does it depend on specifically, like, you know, whether you're doing classification or regression tasks, but even down in like classification tasks, like what you're trying to classify is extraordinarily important in influencing what sort of metric you choose. Now, for classification of performance as well, sometimes it's good to, you know, keep an eye, or, you know, to keep like a decent intuition of what constitutes a good metric. So like, for example, if I got back like a, you know, like a pre-algebra test from 6th grade and that I took now, and I got like a 60% on it, that would be absolutely terrible. But if I got a CMSC 351 test and I got a 65% on it, that would probably be like the highest score in the class knowing possible. So like, you know, sometimes it's good for having a barometer of like what's an actually good score. In some scenarios, like if you're working on MNIST, getting something like a 65% accuracy is absolutely terrible because most models worth a damn can get like above 99. But for novel tasks, like a lot of the tasks that you work on in research, something that's close to an 80% accuracy is actually really, really, really good. In fact, one of the papers I published, we got an 83% accuracy, which I told my boss, I'm like, oh, this isn't as good as I thought. He's like, are you kidding? This is like really, really good. I'm like, okay, cool. Yes, and that paper got published. So it's a good thing of keeping in mind of some sort of barometer of what actual performance means. So not only is measuring performance task dependent in the method you measure it, but also like based on previous results, the actual number you get can mean different things in different contexts. So for the purposes of this one, I'm gonna like, that second point I made, it's important to consider. I'm not gonna bother too much about it because that's really, really, really task dependent in the way of like what task you're using, who you're working with, what the previous research is, a lot of that stuff, and it's honestly up to you. But in terms of performance metrics themselves, I'm going to be discussing three main metrics. One is accuracy, which I'm pretty sure we're all familiar with. One is called AUC, or area under the curve. And the third one is called a confusion matrix, which I really like personally because it's just really nice. With that said, as I've said many times, this is completely not comprehensive. There are an infinite, honestly, an infinite number of ways of defining performance. And every single new paper that comes out, there is oftentimes a completely new performance metric that paper uses itself, and it introduces as like a completely new concept. And one of the main things when you are doing AI research is not only figuring out what a good model would be, but also how are we going to measure the performance of the model, and what facets do we want it to work well. And from there, you can design your own metric that works. So with that said, as I said, it's not comprehensive, so feel free to look through all of them. But first off, let's go through accuracy. As you can see, the slide is very bare because I would like to guess that you guys kind of know what the accuracy is. Just number of questions you got right versus the number of questions that were on the test, really. But moving on from that, what are the pros and cons of accuracy? Well, it's pretty clear to communicate to other people what accuracy is, right? If I tell you that this model had a 93% accuracy on the test set, you don't really need to know what the model is. You don't need to know what the test set's consisting of, mostly, but you can just think, oh yeah, that's a really good number. That's like a A. 93 is an A still, right? Sure. Yeah, we'll go with that. I don't know, you're new to it. But yeah, 93 isn't. So we can go with like, oh yeah, that's like, the model got an A on the test set, so it did well, right? So it's well known and understood, and it's very easy to determine, right? However, accuracy is honestly, it's one of the more, it's a metric that can be used very easily to completely obscure major issues in your data. For example, if I had a medical data set, like any sort of medical data set, 90% of them, well, actually that's a number your end, but most of them, in my experience, have a very high number of normal individuals or healthy individuals, and a very, very low number of the target class you're looking, whether it's a binary classification problem or any sort of multi-class problem where you're trying to diagnose specific kinds of diseases or stages of the disease or whatever. You're obviously going to find much, much, much more healthy examples of healthy people than you are people with these health problems. And as a result, you'll have an imbalanced data set where, like, in extreme cases, you'll have 90% of your data with, label 0 or completely healthy individuals, and you'll have the rest as the remaining 10% divvied up amongst the rest of the classes that you're predicting. Obviously, that's a problem, because then if I make a model that simply predicts 0 every single time, I get a 90% accuracy because I get correct 90% of the time. That sounds good, but then the 90% accuracy sounds good, but when you delve just a little deeper into it, you realize, oh, it's actually really terrible, right? And then furthermore, it requires a homogeneous data set in that, again, it's a similar problem. If, let's say I'm trying to diagnose a skin lesion, right, and my data set is 95% white people, then if I'm accurate for all of the white people and then I fail for every other race, I still have a 95% accuracy rating. And that is not good because, we should be diagnosing skin lesions at an equal rate amongst all humans. So it's all of these factors come to make accuracy a useful metric in very, very, very controlled circumstances. But in a lot of real world circumstances, it's useful in tandem with many other metrics. And another thing that I should emphasize, which is kind of emphasized over, but in general, most metrics are kind of useful when in tandem. So if I have like a good accuracy and like a good, let's say, F1 score and a good bunch of other different metrics, then it's kind of an indication that, hey, this model is actually performing well. If I have good accuracy and the terrible scores everywhere else, then clearly there's something wrong with your model and you should try to fix it. Again, it's entirely task dependent which medley of metrics you choose, but it's important not only that you choose like one, but you choose multiple that can show that your model is actually working in the ways that you want it to. Moving on from accuracy, we have what's called AUC or ROC AUC, or area under the curve, or honestly, there are like 38 million ways people refer to it as. AUC itself stands for area under the curve. What curve specifically? Well, it's called the ROC curve. ROC stands for receiver operating characteristic. The reason that we use the ROC curve, I have no bloody clue. It was used by like World War II people to test radar, and somehow it found its way into machine learning nowadays. But hey, it's helpful. So there is a lot of you can get into a lot of detail on like how the ROC curve is specifically graphed and all of that stuff. but you really don't need to know that. As you can see on the slide, there's an image there. The ROC curve, the y-axis is your true positive rate, so how many times you correctly guess. And then the x-axis is the false positive rate, so how many times you accidentally guess something is positive and it turns out to be a negative. And as you can imagine from the fact that I'm talking about false positives and true positives and all that stuff, ROC curves and AUC in general is only useful in a binary classification problem, meaning that it's only useful when you're distinguishing between 0 and 1. If you have multiple classes, you can't really use AUC specifically for the entire problem. You essentially will have to make you essentially have to make a different curve for every single class that you have, and then do all of that, and then calculate the AUC for each class. And then you sort of like combine it in some various ways that depends on who again, that's entirely dependent on the task you're working on. However, in general, like it's just a pain to do. So frankly, most people, at least in my experience, most people don't about like processing point. But anyway, so AUC is you take the ROC curve and you find the area beneath it. So you just, you take the integral of the ROC curve. And what that tells you is essentially if it's greater than 0.5, that tells you that your model is doing better than completely random classification. You want it as close to 1 as physically possible. 1, if the area is 1, that's a perfect classifier. But again, as you can see on the metric, the farther you are closer to 1, the better that your classification, the better your model is performing. And so as you can imagine from that, AUC scores are in the interval from 0 to 1. So continuing on, AUC, again, its pros are it's better with unbalanced data. You're measuring your true positive rate against your false positive rate. So if you have a really high true positive rate and a really low false positive rate, then you're really good. And it's also better for ranking models. Ranking models means something like a higher insight, right? So not only am I interested in the score that I give someone, I'm interested in that score relative to other examples. As long as those relative scores match up as well, then it's good. So AUC is really helpful there. And the third thing is the visual component. A lot of times in fields like math and AI and stuff, we fail to remember the fact that looking at a pretty graph can actually be really helpful in illustrating how good a model is, as opposed to just saying, hey, numbers, have fun. As much as I love numbers, they're not helpful for communicating that, hey, this is not going to cause people to die. So having that visual component can actually help in solidifying that, hey, this model is working the way that we want it to. Now, cons, as I mentioned, it's not designed for multi-class problems, and most of the problems you deal with are multi-class problems. So it can be kind of a pain. I'm not saying that it's impossible to use. It's the fact I've used it before for multi-class. It's just a bit of a pain and requires a little more of your own intuition there. And it's also semi-obtuse to explain because, like, as I said earlier, I can say I got a 93% accuracy, and like that's easily explainable. But if I say AUC, then it takes a second to go, oh, what does AUC mean? And like, sure, it may make sense for someone like me, but like if I'm talking to like any person and I'm trying to sell them the model, then they'll be like, what is that supposed to mean? How am I supposed to know that's good or not? So it's a little obtuse to explain. However, it's a really useful metric when dealing with unbalanced data sets.
Okay.
Yep.
I think you already said this, but can you give an example of true positive, false positive?
Oh yeah. So true positive would be, say that I have an individual comes in completely healthy, and they go in for like a screening for some disease, right? And say that there's no stages of disease or whatever. I'm not pretty much, so I wouldn't know. So it's just either you have the disease or you don't. Well, a true positive would be, hey, you screen them, you take the test, and it comes back as, okay, they don't have the disease. That's a true positive because they don't have the disease, and you diagnose them as not having the disease. A false positive would be if that same person came in, takes the test, and you diagnose them as, that would be having the disease, right?
Yeah. If
Yeah.
you classify them as having the disease, but they actually don't have.
Yeah, so you classify them as having the disease, but then they don't. I'm sorry, I get this all turned around in my head. But yeah, if you diagnose them as having disease and they don't have the disease, then that would be a false positive because you're going with, oh no, they definitely have the disease, and it's okay. Actually, technically, I realized my first example is wrong. It would be if they had the disease, they come in, and then you diagnose them as having the disease. Because technically, the first example I said is a true negative, not a true positive. You're making this confusing. No, but yeah, listen to what I said the second time. So if someone comes in with the disease and you diagnose them as having that disease, then that's a true positive. If someone comes in without the disease and you diagnose them as having the disease, that's a false positive, right? And ideally, you want a low false positive rate and a high true positive rate because that means you're diagnosing correctly. In practice, which I'll go through with confusion. Actually, you know what? This is a good segue to go into confusion matrices because they help you show all of this. So, confusion matrices. Well, basically, it's a giant matrix that measures the performance of the model over all possible classes. So the x-axis is the actual label, and the y-axis is the predicted label. I know I said they're interchangeable, and like you can see on the slide, I said that in practice they are interchangeable. You can flip-flop which goes on which axis, but like if you do it the other way around, you're wrong. So, personal opinion. It's just what? Yeah, it doesn't really matter. However, at the same time, the way I've seen it more is that x-axis is your true label, and then y-axis is the predicted label. So at least for me, that's how I expect it to look. In general, label your axes, which just goes for any graph you make. Label your axes, please. But with that said, you put the true label on one axis, the predicted label on the other axis, and basically you count the number of examples count the number of examples from a specific label that were classified into a given predicted label. So, for example, you can see if you look at the confusion matrix that I provided here, each column. So if I go to the first column, these are all images that have label 0, and we classified 382 of them correctly as having label 0, 105 of them as having label 1, 96 of them as having label 2, 80 as having label 3, so on and so forth, right? So as you can see from this, the ideal looking confusion matrix is something that is quote unquote lit up along the diagonal, where you have a very, very, very high number of images with a given label that you have accurately classified. If you have if you don't have a confusion matrix that's lit up along the diagonal, then that shows you where your model is breaking down. Because what it does, and that's why I really like them, is it gives you a breakdown over all of the classes that you're working with, and it tells you, hey, where are you failing? So for example, in like an aforementioned medical data set where you have like 90% of normal healthy individuals and 10% of the other individual. If you had just simply accuracy, right? You would only know that, okay, I got 90% if I guessed, healthy every single time. But if you draw up the confusion matrix, you can see that, oh, I'm actually guessing, 0 every time, because it'll show that every single image that comes from class 1, you're guessing it as class 0. And it'll help you sort out these inconsistencies and try to target better or try to weight different classes better so that you can eventually help your model to be better at diagnosing across the board classifying across all the spectrum of all classes instead of just going for, instead of just being good at specifically a couple classes. Now, the confusion matrix is important partially because it's just a really nice metric, but also because I should specify, for those who are not understanding what I meant by saying that we're going to measure your performance by summing up the confusion matrix diagonal, this is specifically what I'm meaning. So if you look at the confusion matrix here, when I say lit up, it's lit up based on the number of examples, specifically on the proportion of examples that are classified into the correct class, right? So the percentages under the little, under the numbers that I have here are what percent of label, or what percent of examples that had a given label that were classified correctly. So in this case, we have 51% class, or about 52% of class 0 correctly classified, around 50% of class 1 correctly classified, and so on. And so ideally, you want it to be 100 on every single diagonal entry and 0 everywhere else. So if I take the sum of that entry, if I take the sum of the diagonal, I want that to be as high as physically possible. So that's what we're going to be doing when we're testing your models, is in order to account for any possible bias in the data set, just because I really don't know the data set kind of.
It's imbalanced.
It's imbalanced. Okay. So to account for any possible imbalances in the data set, if you get like a 90% accuracy rating, that could be good. That could also not be. It depends on it's entirely dependent on your model. And also it could be dependent on the distribution of the data somewhat. So what we're going to do is we're going to sum up the confusion matrix. And if you have a good model that's accurately classifying things, then you should get a really high score. But if your model is failing on specific classes, then it'll lower and lower until, at some point it could be 0, but that'll be fine. But yeah, and yeah, I've written some notes here that like you can normalize it or not. Both approaches are common. When I say normalize or not, normalizing is what I'm talking about, the proportion of examples from each class, whereas non-normalized would just be counting by the simple number and then lighting it up based on that number. The reason I say to normalize it is because usually you're doing this through code, right? And when you're doing it through code, Matplotlib will just assign a color bar based on whatever variables you give it. If you give it a raw number, and like you have like, say you have like 1,000 examples of class 0 and like 100 of class 1, then even if you have a really good confusion matrix, they're that's like, you know, that has 100% and 100% rate of classifying things correctly, then you can have like a really bright square in like the top right, top left for class 0, and like a really dark square because, you know, it's 100 examples versus 1,000. And so it'll like draw the color bar correctly. But if you normalize it, then all of your numbers will be between 0 and 1. So it'll actually draw like a nice color bar. So you can like visually just look at it and see what's going on. And that brings me to one of the pros of the confusion matrix, which is that it's really easy to look at and just see what's going on. I'd argue it's better than a rock curve in that sense, because you just need to look at it and go, oh, is it lit up along diagonal? Nope. Okay, there's a problem there, there, and there. And, you know, fix that accordingly. Furthermore, as I said earlier, it's really good for class imbalance. If you can tell that your model is doing very well in classes 0 and 1, but failing on the rest of the classes because the confusion matrix is just not correct, then, I mean, that's extraordinarily valuable for those things. And also, another thing is you can derive a lot of metrics from those. So like, as I said, we're going to be summing it up along the diagonal. I've had people do a whole host of different confusion matrix metrics. All of them are like, they're kind of up to your own interpretation. Some people will like weight different. So like say that, you know, if I use the disease diagnosis example, if I diagnose like stage 4 cancer as like a healthy individual, then they'll like completely downweight that because, you know, that is terrible. Whereas if it's stage 1 or stage 2 versus stage 1, they'll weight that a little less significantly because I guess to the model it's not as big of a problem, although it's cancer, it probably shouldn't be done anyway. But it's coming down to the same thing of you can generate a lot of different metrics of your own just from looking at a confusion matrix and manipulating it as you want. Cons are, as I mentioned earlier, lack of standardization. So like to normalize or not to normalize, you know, which axis the true label and predicted label go on. It's not really that big of a problem in practice, but like it kind of upsets the visual component because it takes you a second to look at it and go, okay, where is everything and how should I be reading this? And so it can kind of be a pain, but like just do things the right way and you'll be fun. And then also it's reliant on picking big color gradients. I will say that some people go crazy with this because Matplotlib has a lot of different color gradients. And so people will pick something like a rainbow gradient that's like fully saturated on everything. So it'll be like, yeah, so like, you know, white, if it's not doing well, it will be like completely dark blue, but if it's doing well, it'll be like a completely like dark green or whatever. It's like, you make sure that you pick a good color gradient, because as dumb as it sounds, as arts major as it sounds, opposed to, you know, doing CS, it actually makes a huge difference in terms of being able to like visualize your confusion matrix and making it useful for others to read. So yeah, there are more. As I said earlier, there's, you know, all of the ones I listed here. I'm not going to talk about them at all because some of these are complex and some of these just don't really bother. But as I mentioned earlier, ultimately, it is completely up to you to choose the most useful metric for your problem. And like in the future, when you work on AI stuff, it is often, and it is most of the time, in fact, entirely up to you which metric you choose. And once you publish your work, that's when people will go, oh, okay, yeah, your metric's crap. And then it's like, okay, there's nothing I can do about it now, right? So it's up to you to make sure that you choose the correct metric for the job and that you're able to communicate why you chose that metric and what makes it an indicator of why your model is performing well. With that said, that's the end of the model. I'm not going to go through the notebook because I don't want to deal with going through a notebook over Zoom, and here it's just a pain. And also there's like a neural network training thing in there. I'm like, I don't want to mess with Google right now. Enough tech is broken. I don't want to deal with Google possibly throwing a fit as well. So yeah, feel free to look through that notebook on your own time. I will say it's really helpful because there's a function in there for creating a confusion matrix. Copy paste that into your own project notebooks.
Oh, it's already there.
Oh, what, you put it in there?
I mean, no, the project already has code that will draw a confusion matrix for them.
But is it nice?
Yeah, it's blue.
That makes it not nice. I'm sorry, just use different colors. But yeah, no, I mean, you can grab that one if you want. You can use the one Sunrise one. It's just another source for being able to look at how certain metrics work. I think in that notebook specifically, I took MNIST and made it into a class imbalance problem so that you can see the effects of imbalance on something like accuracy and how it shows up in a confusion matrix. So yeah, feel free to look on that in your own time. But with that said, that's it for my presentation. Thanks for looking at it over Zoom or whatever. Anybody have any questions?
You can work in project now.
Yeah, you guys can work in projects as well now. How do I stop recording?
Oh, Wait, no, not here.
It's probably under more.
And stop.